All right, what's up, everybody? Welcome back. So we got some fun stuff lined up for today. We are coming in hot off the heels of our video on the ratio test. And so we are going to introduce another valuable test for series convergence or divergence. And this is the so-called root test. And oftentimes, these are kind of said in the same breath, the ratio test and the root test, because they both involve determining whether a sequence converges absolutely or diverges by looking at limits of a certain kind. So our goals for today: introduce the root test, work through an example of the root test, maybe two examples of the root test, and then talk about some of the strengths and weaknesses of the root test. And as you might suspect, with a name like the root test, we'll be looking at roots, square roots, cube roots. We'll actually be looking at nth roots in our limit. And so here is the test itself. So let's let our sequence a sub n, or I should say our series a sub n, be defined as follows. We can determine the convergence or divergence of this series by examining the limit of the nth roots of the nth term of the series as follows. All right, so we take our nth element of the series a sub n, and then we go ahead and take the nth root of that, right? So if n was equal to 2, this would be the square root. If n was equal to 3, it'd be the cube root, and so on and so on. And I should actually clarify here, I believe there's probably a similar typo in the activity sheet. To make sure that everything is a-okay, we should really throw absolute value signs on these, right? To make sure that we can take, for example, the square root or the nth root of our series, of our term. So with that fix, we take the nth root of a sub n, absolute value of a sub n, we take the limit of this sequence, and we see what that equals. That will equal some value L. And so if L, right, if the limit of the sequence is less than 1, then our series is known to converge absolutely. If our series limit L is greater than 1, then our series is known to diverge. And if the limit of these expressions is actually equal to 1, right? If L is equal to 1, then, as in the ratio test, our root test is inconclusive. So what we see here is, again, just like the ratio test, we will have some drawbacks. If our limit is ever equal to 1, we cannot conclude anything using the root test. At the same time, any series that converges conditionally will necessarily be inconclusive under the root test, right? Because if it converges conditionally, it's not converging absolutely, it's not diverging, and so it would have to fall under this third bullet point. But if we're able to overlook those small issues, then the root test can be very powerful in certain circumstances. And let's see two examples here. Let's clear those marks, and let's see two examples here. So each of these examples, notice, is a series that involves raising an expression to a variable, right, or to our index. So here we have an expression raised to the nth. Here, where our variable is k, index is k, we are raising our expression to the k. And this is really, or these are the expressions where we expect to be able to use the ratio test. Nope, the root test. This is where we expect to be able to use the root test, because the root test will allow us to take an nth root, and that will nicely cancel with this nth power here. So let's go ahead and give this a shot. So in this first example, we know that a sub n, right, the nth term, is n over 3n plus 1 raised to the nth power. And so the ratio test would have us take the limit. I said ratio again. The root test would have us take the limit as n goes to infinity of the nth root of a sub n. So that's going to be n over 3n plus 1 raised to the nth power. And then we would take the nth root of that. So I could write the nth root like this, right? Or I can write it bigger parentheses, raising it to the 1 over n, right? And remember, our indices, or our exponents here, I should say, obey the regular rules of exponents. And so something raised to the nth and then raised to the 1 over n, that will ultimately allow the n and the 1 over n to cancel each other out, right? So according to rules of exponents, raised to the n, raised to the 1 over n, that's equivalent to raising it to the first power. And so let's see that in action here. So this really becomes the limit as n goes to infinity of n over 3n plus 1. And we can take the limit now as n goes to infinity. Notice, because both n's here are raised just to the first power, right? That's just an n to the first, that's a 3n to the first. This whole thing simplifies down to the ratio of coefficients. This limit will just get closer and closer and closer to 1/3. And so that is our limit L in this case. Because L is less than 1, we now know that this series, right, the original series, this original series, converges absolutely, meaning not only does it converge, but if it had positive negative terms, positive/negative terms, then we could throw absolute value signs on here and we would know that that's still converged, right? So this is a series that converges absolutely. As a counterexample, or not a counterexample, but as an example where we have a little bit of a deficiency or where we can't draw a conclusion, let's look at this second case here, right? So in this case, we would have our individual terms, a sub n, are 1 minus 1 over k raised to the kth power. And so if we tried to take the root test straight up, it would become the limit, or we would have to evaluate the limit as n goes to infinity of, we would take a sub n, so that's 1 minus 1 over k. We would throw on absolute value signs if we needed it. In this case, everything will be positive, so we're okay. And then I will take the kth root of that, so 1 over k. Now I'll take the limit as, as k goes to infinity. So in that case, what we'll get, again, the k and 1 over k will cancel out. So that will be equal to the limit, k goes to infinity, of 1 minus 1 over k. And as k goes to infinity, that second piece is going to 0. So this whole thing just becomes a 1. And we get that our limit is 1. Ooh, shoot. That means that this root test is inconclusive, right? Inconclusive. That's unfortunate. So we would have to use some other strategy to try to figure out whether or not this series converged or diverged. As a total side note, this series diverges, right? And here's why. It's actually kind of a cool little argument as to why. This diverges because it fails the good old test for divergence, right? These individual terms do not go to 0. And so the overall series diverges by the test for divergence. How do we know? Let me finish writing this. Test for divergence. How do we know that this fails the test for divergence? How do I know what those individual terms are going to? Well, I can just consider, right, the individual terms. If I have 1 minus 1 over k raised to the kth power, that is actually going to converge as k goes to infinity. That'll converge to 1 over e, amazingly and surprisingly enough, right? It turns out we have done examples like this back in Calc 1 when we were looking at L'Hopital's rule, right? And we were trying to figure out what our limits in indeterminate form would equal. So this example is an indeterminate form, right? This limit is an indeterminate form of the form 1 raised to the infinity power. As k goes to infinity, this gets closer and closer to 1. This gets closer and closer to infinity. So this was a L'Hopital sort of indeterminate form style problem. We developed a whole framework for evaluating those. And if we went through that song and dance and I encourage you to dust off your old Calc1 skills, your L'Hopital skills, and to try to give that an honest effort, just for fun. What we'll see is that this limit actually does indeed converge to 1 over e. So these individual terms are not going to 0. They're going to some small fraction, right, but not 0. And so the overall series must diverge. Fun side adventure there. That's all I've got for you for this video. Have a great rest of your day, and I'll see you next time.